Alright, so today we're going to be going over some equivalent resistance problems. Actually, we'll just go over one in this video, and it'll be a nice way of introducing how to get the equivalent resistance of a circuit. So the circuit we're going to be dealing with today is just going to be a simple circuit where we have a resistor in series with two resistors that are in parallel with each other. So in order to find the equivalent resistance of something, actually before that, I'll just explain what types of equivalent problems we could have. So usually there are about 3 or 4 main types, but you can actually just break it down into 2 most of the time, at least. So here this is the first problem where we have resistors in series and there's something at the end there, and we just need to know what the equivalent resistance is here. In this case, it's pretty simple. Say this is R1 and this is R2. This will just be R1 plus R2. Then there's another situation where you could have this resistor in parallel with another resistor. There could be more, but in this case there's just going to be 2. So we have these 2 connected, and so it could be connected somewhere, but we only care about this. In this case, the resistance would be 1, say this is R1, say this is R2. It would be 1 over R1 plus 1 over R2. Excuse the handwriting. And then you invert the answer. And that would be your equivalent resistance. So back to this guy. We will be going over this guy down here, and we'll be able to tell exactly what type of resistance this gives us. Now notice for the first 2 examples, we were interested in what happened at a specific node, right? And this is the same thing for all circuits. Where you choose that node is important, because if we chose these 2 places, the equivalent resistance would just be R1 as opposed to R1 plus R2. The same thing here. If we chose only these 2 such that it was just here that we were looking for, the answer would be R2. It wouldn't be this inverse expression that we see here. So for this, we have R1, R2, and R3. And as you can see, this is just a simple combination of a series circuit and a parallel circuit. So in order to solve this, we could take it in parts. Now, in this case, we have a situation where you might be confused as to where to start. Well, you kind of have to just look at it and pick a place. You could start from here, but we already know this is R1, so this doesn't really help us at all. Excuse me. This doesn't really help us at all, really. So we're just going to erase that. And then for this, we're going to consider this side. Again, it doesn't really help us, so we erase that, and then we come here. But you might be asking yourself, why don't we go in this direction, right? Why does it necessarily have to be these two first? Well, you see, equivalent resistance is all about taking the parts that share the same voltage, or at least they either have to share the same voltage or the same current. Because when in series, they share the same current, right? Because there's nothing branching out. The current from here, from this side, passes through this object and this object. By object, I mean the resistors, and goes out the same way. So it's the same current that's going through. For this case, it's not the same current, because when the current comes here, because of Kirchhoff's law, the current that goes in through here would not be the same current that goes in through these two edges, right? So because of that, we are not able to exactly say that they share the same current. However, they do share the same voltage. Because let me just draw that again. However, they do share the same voltage, and as you can see, R2 is in parallel with R1, meaning that if we were to cut this place, we would have a potential difference, and they both share the same potential because they're both connected at the same point to the main circuit. So they have to share either the same current or the same voltage. In this case, we go through this resistor. Let's say we have a current I1, and we go here, and as you can see, it won't be the same current I1, it will be I2. The reason being is that current would also need to pass through here for this part, or this component, or resistor rather, to actually get some current as well. Because this would dissipate power, and power requires there to be current and voltage, or current and resistance, or what have you. So with that, we will not go there. So we need to look for the part that shares either the same current or the same voltage. And as you can see, if we cut this part and this part, we would have a potential difference, and both R2 and R3 would share that potential difference. So we can start with this side. Right? And now with this, we only need to apply our formula and we would be able to continue. So let's just say that this gives us R4. So now we have a simpler circuit where we have R1, and then here we have R4, right? So with that, we only need to get this because they share the same current, and we already know that if they share the same current, they are in series with each other. So this would just be R1 plus R4. Now let's use some real numbers to actually check this. So let's say we had the same circuit, and right, so we had the same circuit, and let's say this was 2 ohms, this was 3 ohms, and this was, say, 5 ohms. Probably should have made them all 1, but we'll just go. So we'll go with our procedure. We know that this shares the same voltage, so they're in parallel. 1/3 plus 1/5, and then you invert it. Now I could do this on a calculator, but I'm gonna try this. So we have this here, this here, it is pretty slow. Alright, so actually that would be 5. And then this would be 3. Alright, so we have 5 and 3. It is switched, but it's the same thing. So as you can see, we get 1.857. So we have 1.857 here, and then with that we have 2 ohms in series with 875. And now that this is in series, we only need to add them, and I can tell that it's 3.875. Now we can easily check that by refreshing this page and saying resistor there, resistor here, and then that would be 2, that would be 3, and that would be 5. And as you can see, 3.875. So there you go. Yeah, it's not really hard, at least for this case. There are a bit more difficult problems involved with equivalent resistances, but so far these are pretty simple. In the next video, we will be going over more complicated circuits that involve complicated shapes like these, that when put in a larger circuit, you can't really divide it into series and parallel. You would find out that this is also an easy or a different version of this configuration. And we'll also go over this as well. Alright, so I hope you enjoyed it. Oh, just for the sake of all the people interested, this is called a delta to Y. Actually, this is the delta configuration, this is the Y. And when you convert between, it's delta, delta Y transformations. It's pretty easy to do, and yeah. One more thing is complicated circuits, or seemingly complicated circuits, like cuboids, so there's also in the back, hopefully you understand. There are resistors on each edge, and we're trying to find the equivalent resistance of this. Note that in order to find equivalent resistance, it's, as we said before, it is important what our reference point is. So the equivalent resistance between these 2 points would be different from the equivalent resistance between, say, this point and this point.